So in fact, I wrote this note 2 months ago, and the purpose for this note is to help Yongjian organize the papers and he may need for his next project. So this is the original purpose, but at this time, I think he has already almost finished the pipeline of his projects. So I'm not sure whether it is useful or not for this note.
Yeah, you can just go through, and we are I'm sure we can get some insights from there.
So okay, so I will get started. So for this note is to summarize some variational autoencoder and how it's applied to the single cell data, and then introduce the graphical variational autoencoder and how to construct a graph view the variational autoencoder. So these are the four papers in this note. So first, let's quickly review the variational autoencoder VAE. So this is a generative model. The purpose is to generate the data. So here's for the generative model. So first, given the data set X here, and we'll assume this is the main assumption for this model. So we assume that the data are generated by some random process involving an unobserved continuous random variable Z. So here Z is a latent variable. And denote the P theta Z as a prior and P theta X given Z as a likelihood. So we can only observe X, we can't observe Z. And here theta denoted as the true parameter here. So here theta star is unknown. So we don't know the true likelihood and the true prior. Because we don't know the true P theta here, so instead we introduce a recognition model Q phi Z given. So we introduce the recognition model Q phi Z given X. So here this which is an approximation to the intractable true posterior P theta Z given X. So the true posterior given prior and the likelihood, the true posterior will be P theta Z given X. And usually we count this posterior is usually intractable. So instead we use a approximation model here, Q phi Z given X. So here our approximation model has parameters phi here. And then consider the marginal likelihood of our data xi. So if we have n points, then the log likelihood will be the summation of the log likelihood for each point. And then for each point, we can write it as two terms. First is a KR divergence, and the second is the elbow evidence lower bound. So I skipped the algebra to how to get this equation. So we only need to know that. So the marginal likelihood can be rewrite as two terms. The first is the KR divergence, and the second is the elbow. The purpose usually for the statistical model, the purpose is to maximize the elbow. Maximize the log likelihood. But in this case, since we directly maximize the log likelihood will be difficult, then usually instead we will try to maximize the elbow here. So this is evidence lower bound because the KR divergence is always positive. So the L here will always be the lower bound of the log likelihood. So this is the reason that it's called the evidence lower bound here. And then for the evidence lower bound, we can rewrite like two terms. First is a minus KR divergence term between Q phi Z given Xi. So this is our approximation model, and then the prior P theta Z, and then the likelihood under the expectation of the log likelihood over the approximation model distribution. So I also skipped the algebra here. And for the VAE, the purpose is to maximize the elbow, that is to maximize theta and phi to maximize the L here. So we have two parameters. First is the variational parameter, so which is phi, and the next is the generative parameter, that is theta. And here we have two models. First is it's called the inference model or the encode model. That is given x, we encode it to the latent variable z, or we do the inference, that is q phi z given x. So this is again, this is the approximation model for the p theta for the posterior here. And the p theta x given z. So this is a likelihood before. This is called the generative model or the decoder model. So for the generative, that is because we assume the generative model is the data is generated from some latent variable z. So this is called the generative part. Given z, then how to generate x, or to compare with the encoder. So this part is called the decoder model. So for VAE, we only need to summarize two models. First is the encoder model. Second is the decoder model. And then based on these two models, we can maximize the elbow. Then it's done. Next is a quick example about how to use it. So this is the most famous example, and usually many applications use this kind of framework to do the VAE. For the general VAE, we can use any encoder model or decoder model only if we can maximize the elbow to get the parameters. But usually we will apply this model. So first, suppose the prior is this one, the standard normal distribution. So the true prior we won't know, but usually we will assume it's a standard normal distribution. And we assume that the variational approximation prior, that is the inference model, or encoder model, has a multivariate Gaussian form. So this form we can define any form of this inference model, but usually we will choose the normal form here. So in this case, we have two parameters, mu and sigma here. So these are the outputs of the encoding neural networks. So if we propose two normal distribution here, then the first term, the Q divergence between the prior and the approximation model will have explicit form. So this is the reason because of two normal. And for other distribution, we may not have the explicit form. So this is the reason that normal is easier to apply. And based on this model, then for the second model here, the decoder part, then usually we will use the Monte Carlo method to estimate the expectation, and to optimize the neural network, then we need to use the repersonalization trick. Because to use the Monte Carlo method, so that is we need to sample Z from this distribution here, and recall that this is a normal distribution. So if we have mu and sigma, then we can sample Z from this distribution. And then we can calculate our encoder model based on 0Z, that is this form. So this is how to use the Monte Carlo method to approximate this term, but we can't use this directly, because if we sample Z, then Z depends on mu and sigma here. Then is Z. If we sample Z directly, then the sample will depend on mu and sigma. Then we cannot use the back propagation to do the optimization. So in this case, we need to use the repersonalization trick. That is, we sample standard normal distribution epsilon here, and then calculate Z from based on this mu plus sigma epsilon. So if epsilon some from standard normal, then they will follow distribution with mean mu and variance sigma square. So based on the epsilon, we can calculate the z, and then we can calculate the approximation for the second term here. So for this form, then we can use a backpropagation to optimize mu and sigma. And a similar method can be used to approximate the gradient. So if we use gradient descent, then we also need to calculate the gradient of this term, and the gradient of this term can also be calculated based on the Monte Carlo method and the reparameterization trick. Yeah, so this is a standard example here. And so do a quick summary. So to say a VAE model, we need to note three things. So first is what is the generative model? That is, what's the model for the Q phi z given x? So usually there will be one neural network here. And in this case, we need to use the neural network from x to mu and sigma square. And then we know that they will follow the normal distribution with mu and sigma square. And the second thing is generative model. This will be another neural network usually, and it's given z how to implement a model to get the x. So in this case, it will be a neural network given z, it will input it will output x. So for example here.
A question.
Yes.
So in this framework, so only p theta x given z is a neural network. Right?
Q phi z given x is also a neural network, but the output here, the procedure is to given x, we need to calculate the mu I given xi. We implement a neural network and then output mu I and sigma I square.
So mu I and sigma I square is two output of a neural network, and the input is xi.
Yes.
Right.
Yes. Yes. And z is sample from this distribution. So the latent variable z samples from this distribution. So we have two neural networks here. Yeah, and
oh yeah. Another question. So for p so for the form of for the form of p theta x given z. So because it's I think it's a density function. So how to like build a neural network for this without give it a form? Yeah. It's like he also gave like a normal form with a theta. Because this is because for example for Q phi, so the parameters are set as the output of neural networks, then that's okay because that's an output, but by plugging this output, so we get density. Yeah, but how for p theta? So because p theta is also a density function.
Yes, we also need to assume we need to assume the form of the p theta. We have similar form here that we give a parametric distribution model, and then the parametrics got from the neural network.
We still need to set a parametric family for p theta, and then the parameter are tuned from neural network.
Yes, so we can say the next.
One question. I have a question about this. So I was wondering, like for the models with the latent variables and the encoder and the decoder, can we say those models we are studying the explicit probability distribution? Because in your first equation, actually we are still doing the maximum likelihood, we are not estimate the log likelihood of the p theta of x. And we cannot get it, so we are studying the lower bound of this. So after we train the variation autoencoder, we still don't know what the form of the p theta x.
So, we propose some form, but we don't know the exact form.
So can we say we know the p theta of x, or we don't know? Because we can generate samples.
Yeah.
But we train encoder and encoder and the decoder of two different distribution with our assumptions.
Yes, so in the final, I think we don't know the true form, but we have an approximation form.
Yeah. So
we don't know the true generating distribution, but we give an approximation for p theta x.
So we still don't know the we don't know the exact form of the p theta of x in really explicit form, right? Okay, thanks.
I think it's better to say that we have the approximation explicit form, but we don't know the true explicit form. I think this is much precision. Yeah, so this is for the standard VAE and the most famous example. Yeah, so just a quick summary. So we need to know we need to propose a prior for the latent variable given the form of the inference model, and also given the form for the decoder model, and then we can base it on the prior and encoder form. We can have the Kerr divergence, and based on the decoder form, we can calculate this term. So just focus on these 3 or 4 things. So next example is about how to. This is a paper applies variation autoencoder to the single cell data. So we can focus on the several terms that I mentioned before to check how this model works. So for the single cell data, so the generative model they consider is a zero inflated negative binomial model. So zero inflated negative binomial. And let n be the index of the cell and g be the index of gene. So first term is a prior. In fact, here, this model has 2 prior. First is ZN, which is a latent model before, which is sample from standard normal distribution. This is standard. And second is LN. LN here is library size for the single cell data. So suppose because it must be positive, so suppose it's sample from it's sampled from log normal distribution here, and then based on the ZN here, it introduced the generative model as 0 steps. So first, given ZN, we can use a neural network to get the rho n here. So rho n, which is used to get the WNG here, which follows a gamma distribution, and based on that gamma NG, we can, and suppose YNG follows a Poisson distribution. So in a word, for these two distribution, Poisson mixed gamma will be a negative binomial distribution, and based on this, then YNG will follow a negative binomial distribution with mean, LN, WNG, and variance or standard deviation rho NG here. So this is a generative model and how to use GCN to generate the gene expression level YNG. And next part, this part, it will be the zero inflated part. So given GCN here, first we generate HG. So this is a probability. So we use a neural network FHG here to get the probability, and then use the Bernoulli distribution to generate HNG. And then for the observed gene expression level, it will has two terms. First, if HNG is equal to 1, it is equal to 0, then we have YNG, otherwise it's equal to 0. So combine these four, we can say that this is a zero inflated binomial distribution. We have a zero inflated term here. And in this case, X, so here, X, based on this four, X and G will follow the CIMB distribution with mean Ln rho n G. This is the mean, and the gene specific dispersion theta G here. So this is a native. This is a native binomial part, and also the zero inflated part per probability FHG CN here. So this, so here combine this all these terms. So X and G will follow the zero inflated native binomial model with certain parameters. Again here, in this case, for the generative model, that is from Z to X, we have two neural networks. First is FW, which is used to generate the rho, and second is FH here, which is used to generate the probability. So this is the generative model and the prior. So the since left will be the inference model. So here, usually in the variational inference, we will propose the mean field assumption that is Q phi Zn Ln, they are independent given Xn. That is, the inference model will be Q Zn given Xn and Q Ln given Xn. And we also assume that in this case, QZN given Xn will follow the normal distribution. Then we can calculate the QR divergence directly because Zn follows the normal. And the QLN Xn follows the log normal distribution. Then we can also calculate the QR divergence between the prior here, PLN, and the QLN given Xn. So now we have the generative model, we have the inference model, we can calculate the explicit form for the QR divergence. And then we can use the standard VE method here, the Monte Carlo method and the repersonalization trick to get the elbow and then do the maximization to the elbow to get the parameters. So yeah, so this is a SCVM model. Any questions here? Yes, good. So in the following, I will only focus on the inference model, generation model, and the prior. Then all the procedures are same as before. That is to calculate the QR divergence and use the MCMC and use the Monte Carlo method and the repersonalization trick to calculate the elbow, and then to use the gradient descent to optimize the elbow. That's all. Next is a graph convolutional network. So this is to for this part, it's just to quickly introduce how the graph this section is just to introduce the form of the GCN, the graphical convolutional network. So given some intuition, that is when we do the manifold alignment, then we can use the Laplacian laws. Then is L is equal to Fx transpose L Fx, which can be written like this. So A here, usually we denote it as an adjacency matrix. If Aij is 1, which means Xi, Xj are connected. So, and here we want to find the form of F we want to find fxi, fxj, so which is a lower dimension representation. And here L is a Laplacian matrix is equal to D minus A here. And for the multi-layer graph convolutional networks, we will introduce one form for F, that is this one. So that is F is a multi-layer GCN, and for each layer, it has this form. So suppose HL, L from 0 to capital L, and H0 will be Xi, and tilde A is a symmetric normalized agency matrix, and WL will be the matrix here, and sigma is the nonlinear function for the neural network. So this form is called the graph convolutional network, A, H, W, sigma. And then we can use multi-layer to define our function F here. And the reason for this form based on the graph Fourier transform, which I don't know. So we only need to remember that for the graph convolutional network, we always will have this form. The agency matrix times the data times the matrix, and then have a composed with a nonlinear function sigma, and then do multi-layer. So this is the graph convolutional network. And based on the graph convolutional network, we can define the variational graph autoencoder. So in this case, again, we need to focus on the inference model, encoder model, decoder model, and also the pri here. And usually the inference model or the encoder model is completely same as before. So that is given X and A. So here A is a genesis matrix, X is our data, and Z is a latent representation, so which are same as before. And QZ given A, which follows the normal distribution here. And we impose the mean field assumption that given X and A, then each Zi are independent. So here we have this form. For each Zi, which follows a normal distribution. And for the normal distribution here, we have two parameters, mu and sigma square, and they are from the, instead of from the standard neural network. So here we assume that they from the graphical neural network. So which is from the GCN. Recall that GCN has this form. And in this paper, they use, for the GCN, they just use 2 layers. So that is tilde AX W da. So you can see that for each layer, it's exactly same as this one. But in this case, we have 2 layers. So that is, instead of the standard neural network, they use the GCN to estimate U, mu, and sigma here. And again, it is a symmetrized normalized genesis matrix. So this for the encoder model. For the decoder model, so in the original VAE, the purpose is to generate the autoencoder is to encoder, from encoder we can get Z, and then from decoder we can get X. But the difference here for the graph autoencoders, the purpose is to generate the graph A here. So in this case, the decoder or the generative model is used to model A given Z here. And they use the standard, the simple linear product between 2 latent variables to define probability PAIJ. So then is PAIJ is equal to 1 given ZIZJ, which is equal to the, here is just the inner, based on the inner product, sigma ZI transport ZJ. So this is a generative model or the decoder model. And then again, the purpose is to maximize the elbow here. The kill the alternacy, which is normal, so we can calculate. And then for the second term, we can again use the MC method and the repersonalization trick. So this is for the variational graph model. And the last model is, I think Yongjian's project is based on this model. Yeah, and the last paper, the reason we introduced this paper because we do the presentation on our course statistic graphical model. So I also want to mention this paper. So for the previous paper, the input will include the adjacency matrix A, and the output is a latent variable Z. So for this paper, the reason is how to generate the graph based on X and Z. So the difference here is that A is not an input, A is the output, A is our purpose. We want to generate the graph A. So first is the standard VAE structure. The motivation is from the structure linear, is from the linear structure equation model SEM. So then this is SEM model, and A is a adjacency matrix. We have data X here. And Z is a noise vector or the latent variable. And then X can be written like this form. And in this paper, they propose a new graph neural network architecture. So for the generative model, that is from Z to X, suppose it has this form, F1Z, 1 minus A transpose inverse. If we pick F1, F2 as an identity function, then this will go back to the linear structure model, linear structure equation model. So this is a generative model, and this is a decoder model, encoder model. So decoder model, encoder model, and then we can write like the elbow as has this form. And for the prior, we will always propose a standard normal distribution, and QZ given X will be the multivariate normal distribution with mean M and S here. And we also assume PX given Z is also a multivariate Gaussian with mean MX and SX. And then in this paper, they define F1, F4 as identity matrix, and identity mapping and F3, F2 are the neural networks. So we have almost completely the same model as before. Instead, we given a specific form of our generative model and the decoder model and the encoder model here. And then based on this, we can use a completely same method as before to maximize the elbow. So up to now, we haven't talked about any constraint about the DAG. So here we want to learn A, but in this paper, they want to learn DAG A, that is a directed no circle graph. So in this case, we haven't added any constraint for A here to make it no circle and to make it as a DAG. So in this case, they add a constraint here. So that is by the theorem in this paper. In another paper, it has a beautiful theorem says that. So let A be the weighted adjacency matrix of a directed graph. Then the graph is a cyclical, that is DAG, that is a directed no circle graph. If and only if it has this form. If it satisfies this condition, then A will be a DAG. So then it transformed from the based on this constraint, then we can transform to learn DAG. We can transform the problem to a continuous optimization problem, and then finally, the final learning problem will be minimize minus elbow. So we want to maximize the elbow, so which is minimize minus elbow for A and theta, and A is a adjacency matrix will follow this condition. So this condition is to make that A will be a DAG. So the method to solve this optimization problem is a augmented Lagrange method. So I skip this. So this is one method that is how to use the VAE to base it on the DAG constraint to learn a graph here. So yeah, this is the first paper. And finally, just some discussion and some ideas. So
Yeah, I have some questions for for the last one. So for this constraint, so he used the augmented Lagrange method. I just think because I forgot it, so I think so since this HA, I think because it include I think the M here. Yeah, I think it's not a linear constraint of A. So even we use argument Lagrange method, so maybe we cannot get A that follow this constraint. Yeah, right.
I agree. I think in this
Yeah,
paper,
I mean,
provide
is there any some because I do not read this paper, so is there any some part like after we get this A, we use some post progress to change this A to like uncircled and uncircled graph. Yeah, because
yeah, I think this is a good question, but I don't remember this paper talk about this. Yeah, maybe they will talk about it in the simulation, but for the model part, they didn't talk about it.
okay. So another thing, let me check. So what is F1, F4, and F3, and F1 to F4? So the F1 and F4 are identity mapping. So it just means we can just remove F1 and F4. Yeah, okay. So then F3 and F2 are neural network. So it's like a Z after transformation included with this graph, and then we put it into a neural network. Then okay. But we also need to learn A. So okay, let me see. So A is also treated as a parameter. So for X and Z, just like a graph neural network, so we take it as a layer.
Yeah. Just a standard graph neural network, but with this term, so motivated by the linear structure equation model.
Also, do you use this method in your paper?
No.
Because I know you are doing some DAG, some work on DAG.
You mean the project with
yeah
with Dr. Let me see. I think we don't use this form.
Guanxun, can I ask you a question?
Yeah.
What's the reason that you convert a graph into a DAG?
What do you mean?
Because the last part you set a constraint, right? You make this graph you generated as a DAG. So what's the reason that it has to be a DAG?
Sometimes if we want to know some, I think for example, maybe in the single cell data for the gene agenesis matrix, sometimes we may want to know how the then it's one gene will influence another gene. In this case, we may want the directed graph. And in this case, we may want to have a DAG. But I know that this assumption usually doesn't satisfy in the biology because usually there will be some circle. But DAG will somehow give us some feeling about how some gene will influence the other gene. That is, compared with the undirected graph, for example, from PCNet, one advantage of DAG is to learn the direction. So from the direction, we may somehow get some information.
So it will be like easier to interpret the result.
Oh yeah.
Yeah, that makes sense.
It may give some causal relationship.
I see. Thank you.
Yeah, guanxun. The last part, I have a question. So in what cases we can consider SEM as our model?
Huh?
In what cases we can consider SEM as an appropriate model for example, constructing the adjacent matrix?
I didn't see the point.
I think we made an assumption that the adjacent matrix follow this formula, the SEM, the X equal to the first one, adjacent matrix transpose adjacent matrix multiplied by X plus some noise. And without this noise, the adjacent matrix is just an identical matrix. So
not identical, I think. I think SEM is a causal. It's a causal. It's a model of causal inference. So this A do not, even we do not have Z. Yeah, this A is not identical matrix.
Yes.
Usually
we can suppose we know if we know the order of X, then A will be the upper lower. A transpose will be the upper triangle. Sorry, lower triangle. Then it is, for example, X2 will only depend on X1, and X1 will depend on from X1 to X minus 1.
Yeah, if we know the order, that will be.
Yeah, so this will be a DAG. That is to show the causal relationship.
So Yongjian, so do you use the third paper, the idea of third paper in your new project? Oh, actually, I do not know what's your new project.
Yeah, maybe next time I can do a prediction about it. It's just we want to simulate the effect, the potential effect of the knockout. So we use the variational graph autoencoder to train a wild type data, and then we manually knock out the edges of the target gene, and then we feed the manually made adjacent matrix to the train model to see what has changed.
So you want to simulate a graph? Yeah. So okay. That's why you build a generative model for graph. Yeah. Right. Okay. Thank you. Yeah, because I'm trying to do some work like the fourth one. Yeah, like to generate the graph or the graph from data, but maybe not DAG graph. Maybe not DAG, but just some correlation graph or some neighborhoods graph. Yeah, but.
So if there is no question, I will stop here. Okay, thank you.
Do you have any ideas how to use the things you introduced?
No, it's your project.
Yeah, I got it.
I just
I just want to. I just want to share that. I mean, there is one group in my current university, and they are starting on the single cell data. And recently, they focus on two group of things. The first thing is like how to integrate like multi-well or omics data. So, but I do not want to focus on that. But for the second one is the second group of group of works are on, I think what Dr. Tsai what the second idea of Dr. Tsai is something include the spatial the spatial I think this transformic data. I forgot how to how to say it. And just like the single cell data include the spatial information of of where it is in the organization or something like that, and how to recover the relationship of different cells. Yeah, something.
Mm. Mm. So any other comments, questions, suggestions? Okay, I will stop here. And Eugene will talk about another generative model again.
Yeah. So I'm gonna share my screen. So everybody can see my screen. Yeah. So so I will briefly.
Can you make
Sorry?
it bigger? Can you make it? Sorry.
Bigger? Bigger? You want
yes.
bigger or smaller?
Bigger.
Bigger.
Okay. Okay.
Yeah, it's too big for me, but yeah. So I will briefly introduce the concept of the generative adversary nets, also known as GAN. So it's quite old paper. As you can see, it was published in 2014. It's almost like 8 years or 8 years ago. But still, the GAN based generative models are arguably outperform other generative models in the industrial applications. So it would be good we have some get some insights from there. So this paper was written by this guy, and now I think he now is kind of an adjacent researcher from Google. That if I didn't make a mistake.
Oh,
so in the yeah.
He go to Apple now.
Oh, he went to Apple now. Okay. Yeah, whatever. So in the abstract, so we will firstly go through some sentences. So basically, we in this generative task, we simultaneously train two models. So we will train a generative model we denote by G that capture the data distribution. So we can generate the real data. I mean, that's the task of this generator. And we also have a discriminative model. It's a discriminator D that estimates the probability that the sample came from the training data rather than the G, rather than the generative data. So there is a famous analogy for this for this game theory game. We can just imagine that the discriminator is the police and the generator like a counterfeit, which means it's a person who is going to like try to fabricate the fake money, for example, and the police is try to tell whether it's the sample he got is from the fabricate fake money or the real money. So it's a game between these two guys. And through the process of training, through the process they interact with each other, they grow up together. The police become more familiar with the fake money and the generator made. And the generator from the feedback from the police told him or her, the generator will learn the strategy how to make the fake money better, to fool the police, to cheat the police. So So like this sentence said, the training procedure for the generator is to maximize the probability of D, the discriminator, making a mistake. So it's just like the analogy story said, the counterfeit, the bad guy tried to fool the police, making the fake money. And okay, that's the basic motivation of the GAN framework. And if we look at the loss function explicitly, it looks like this. So it's a min-max game. So we have the form of this value function. This is called a value function. So we have the actually this will look like this. So suppose we have real data follow some real distribution P data from some distribution P data, and we are actually going to sample some noise from Z, and we have our generator from this just a noise data Z. This would be our fake data X hat, and we input these two to our discriminator. So discriminator will tell whether this X or whether the sample from the real distribution P data or some fake data, we call it P generated PG X, whether it's from the real distribution or the fake distribution. It will tell you whether it's real or whether it's fake. So the framework is look like this, and so our first task for this for the training is to maximum the likelihood, maximum the value of this equation. So basically, we will sample some real data from our real distribution, and we want to maximum the likelihood, log the likelihood of the discriminator make a right decision, right? Because this data is the real data, and the dx would be the probability that the discriminator think the real data is real. So the second term is we sample some, suppose we have some prior distribution. So here in this model, they just define this Z is the noise, follow some normal noise distribution. So we have our Z, and we train our generator. So this G of Z would be our X hat. So X hat actually is we label it as fake data. So D of G of Z would be the probability that your discriminator think the fake data is real. So 1 minus this would be your fake data that your discriminator think is fake. So it makes sense in this form because your discriminator's task is to make the real data think the real data is real and the fake data is fake. So you maximum the likelihood that the discriminator makes the right choice, make the right decision. And after you train your discriminator, you get, for example, after a couple of iterations, you get a really good discriminator, and it can tell whether your sample from the real distribution or the fake distribution. And in the next round, you want to train your generator. So generator is you can think it's a bad guy. So as you can see in the first term, nothing has to do with the G. So we just ignore the first term. It would be the constant term in the optimization training the generator. The second term, because the generator, you want to fool the discriminator. So instead of maximum the likelihood of this, we want to minimize the likelihood of discriminator make a right decision, right? If we minimize this form, which means the generator is really good at making fake data, and it can fool your best trained discriminator, and it cannot make the right decision. It will think your fake data is real, which is wrong. So this is the explanation of this loss function. And do you have any questions about this? Yeah. So here is a figure showing some training process. So this one, this blue dashed line, they denote as a discriminator, and they denote this is the discriminator, and this is our real data, and the green line is our fake distribution. The distribution generator learns, and the distribution that trying to mimic the real distribution P data. So after, as you can see, after a couple of iterations, the PG, the fake distribution, will converge to the real distribution P data, and your discriminator would be the constant. So this value would be 1/2, because it makes sense, because your discriminator cannot tell whether it's true or fake. It just tell 50% is true, 50% is real. So it doesn't have any power to tell the truth. So which means your generator really good at generating the fake data. It's just a fool your discriminator. So that's basically how the process run. And in the part 4, they have some theoretical results. They have some math proof how what's the global optimal of this loss function of this mean mass game. So before I dive into the algorithm, I will look at this. They argue that the global optimal solution is that your PG, the fake distribution that your generator mimic, would converge to your real data distribution. So after you PG, so in the first theory, they said that if you G fixed, the optimal discriminator D is look like this. So and they have some proofs. So I'll skip that. So if you have the DG equals to B data, your optimal discriminator would equals to 1/2, because this one equals to this one. And what else did I have? And they also said the optimal value of this loss function would equal to minus log 4. So this log is the natural log. Why? Because you just plug in the 1/2 your best discriminator value 1/2 into the loss function, and it will be calculated as as a minus log 4. So this is the minimum value of this loss function, which means you achieve the optimal generator and the discriminator. Your discriminator value would always be 1/2, and your generator would always generate the data that looks like the data sample from the real distribution. Yeah, so that's it. And the algorithm is not complicated. Basically, it has two. In one iteration, basically it has two steps. The first step is you train your discriminator. Sorry. So this part is the one that you train your discriminator. Basically, because it's you want a maximum. Sorry. Yeah. Basically, it just apply the gradient descent. So we compute the gradient of our value function like this. And the second step, after you train your discriminator, the second step is your train your generator. So basically, it's still the stochastic gradient descent. You compute the gradient of your value function, but in this training, the first term has nothing to do with the G, with the generator. We just focus on the second term here. And for the complexity, for the speed of achieving the convergence, this just suggests at least k equals to 1. K means the step that you train your discriminator. And in their empirical result, k equals to 1 surpass the performance. So you just train your discriminator once, and then you train your generator, and again you train your discriminator and train your generator again and again, and they will both become better and better. So that's pretty much about GAN. And something I have to say is usually like people argue that why although there is an evaluation matrix to evaluate how the generative model perform, we can just tell from for example, we just tell from the image that this is GAN generated and this column is the variation autoencoder generated. We don't have a really quantitative metric to compare these two, but we can tell from our naked eyes. So maybe this one is more, the images are more sharp, are more clear. But people argue, I mean, previously they argued that the reason why is that because GAN use the JS divergence, it's a JSON channel divergence instead of a KL divergence to train the model, but actually it's not. I think personally, I agree with the argument that variational encoder, we made a really strong assumption on the latent variable Z, because the Z follows some multivariate distribution with really constrained sigma. That sigma doesn't that sigma is a diagonal matrix, and it will lose some information, really important information, our real data. That's basically the comparison between GAN and the variation autoencoder. And another thing is the generative model, the GAN also didn't learn the probability distribution P of X in a really explicit form. We didn't know anything about P of X. But we can sample from the Z. We know the generator. We can sample X from the G of Z, and that's basically the trick of I think most of the neural network-based generative models. And what else? Yeah, and also there are some programs associated with the GAN, so they have, it has been involved in many years. For example, the most famous one is the vanishing gradient. So suppose you train your discriminator really great. You train a really best, you train the best discriminator, and the dx and the 1 minus dx would be 1, right? If you have, for example, your x is the real data, and the d of x would equal to 1 if this d is really great, and the x is fake, and the d is really great to tell it's a fake, so it would be 0. So 1 minus 0 would be 1. So this loss function would equal to 0. So in this case, we lose the power to continue training our generator, because your loss function or your gradient equal to 0, you cannot compute any gradient anymore. So that's pretty much about GAN. Do you have any questions?
Yeah, is this the original paper introduced?
Yeah, it's the original paper.
Which year?
The paper from
Okay.
A year ago.
Pretty new. Okay.
Yeah, it was cited more than 33,000.
Mm-hmm.
So I will, if you don't have a question, I will stop here. Yeah.
Can I ask a question?
Yeah, sure.
So as far as I know, this GAN is pretty hard to train, right? I mean, it's
yes.
You don't know how to. I mean, if you want to use this GAN to generate some RNA-seq data, you don't know if your generator provide you some data that is very close to the real one, right? Because you don't know how to like, it's not like image. You can just you can just see the difference between the fake one and the real one. The RNA-seq data is like kind of hard to distinguish, right?
Yeah.
So how do you apply this kind of technology to your research?
Yeah, that's a good question. I think the reason why I revealed the mechanism of GAN is because the research that Dr. suggests, and I think the research from Dr. Shen's group, they focus on the use of the GAN to do something with the protein. And so I think it's a good time to review some technical about this. And for the RNA-seq data, I didn't realize any research used the GAN to generate the RNA-seq data. And yeah, as you suggest, it's really hard to evaluate how the generated data is good or not.
Yeah.
Yeah, so this is the problem for the supervised learning. You need a big data to train it. We don't have a good training data for any of our single cell data. But the idea is interesting. So you have a adversary, means a conflict. It's a confliction between two players. Yeah. Let me think. Can we just learn one network and see from time 0 and then compare with the time 1 and time 2 and see, okay, I can predict using information from a time 0 network and what's the time 1 network will look like, and compare, because you have your prediction and you have your all real data constructed. We just create the 2 players and the 2 I don't know, maybe.
Yeah, I will maybe read more papers and
yeah, you compare the predicted network with the real network in the next data point time point, and then based on the comparison, and you change your parameter in order to generate a better network to fit with the observed network, and just iterate a couple of times and then make a better prediction for time series networks.
Yeah.
Okay, I think that's all for this week. So recently, I also very interested in the DMD. So it's a dynamic mode decomposition, and there's a link. I have a quick summary of what it is. Yeah, so that's something which you don't rely on training data. So maybe more straightforward to apply to some of our data. This method is really good for detect the dynamic if you have some fluctuation, and you have to have a circle in the data in order to detect this higher low frequency iteration in the data. In single cell data, we probably don't have that. Other than the cell cycle, you may have a cell cycle in time 1, time 2, time 3, different stage of cells. Each cell still have this cell cycle itself. It doesn't matter which stage of your cell it's in. Maybe so you can use some of this information here. And next time, maybe we will have some quantum computing one-on-one lecture again. So make sure everybody on the same page. Otherwise, it's only Christine and myself. He's taking a class, of course.
Yeah, next time I can present something about quantum
Yeah, so
computing.
just like people know, okay, how this very basic. It's quite different. I mean, completely different thinking.
Yeah, for sure. Next time
Okay.
I will present.
Yeah, it's good. So, Zhuyan and Guanxun, take care. You are negative. We're probably all positive right now. It's kind of a nature protection of ourselves.
Take care.
So I don't know how people know which strain they're getting. Maybe it's Omicron, maybe other strains. We have no idea what's around us.
Yeah, I had a test last Tuesday, but I'm still waiting for the result.
Yeah.
Yeah.
And this Winter Olympics is going to happen very soon, and they create a closed cycle, so nobody will contact with any athletics which participants in all these players. So they isolated everybody from the general public in Beijing. So anything happened to the athletics, it will be on their own. So they are at risk, actually.
Yeah, because the Winter Olympic is coming.
Yeah, it's coming, and it's coming. you may bring the new virus strain out.
Yeah, and
maybe introduce. I don't know what will.
Yeah, and today Beijing Beijing come out a new policy that so if there are, I mean, just for the other areas of China, so if there are some cases, so in that area, so if you want to go back to Beijing, so they will force you to go back to Beijing before the Olympics and yeah, so
then you will stay in Beijing.
Protect. No, yeah. Also, the people who want to go back to Beijing, they cannot. Yeah. If the place they live in, they currently live in have some cases detected. Yeah. So he do not want to bring any risk to Beijing. Yeah, but that's just for but that's not for the for the people who attend the Olympics. Yeah, just yeah.
Mm-hmm. Yeah, I'm just scared of the new virus will come out after the Olympics game, because if you have new strain, it will be introduced to all of the other part of the world, and because the zero clean policy in China, so this is outgoing so it's scary, and we will never finish this. Okay, so let's see, and what will happen in the next 2 weeks. We'll meet at okay. Take care.
Take care.
Okay.
Bye.
Everybody
Bye.
take care.
Bye.
See you next time.
See you.